In this video, we're going to be talking about surfaces. You should have seen a bunch of these in Knots and Surfaces course, but we're just going to have a quick reminder here. So these are going to be interesting examples that we'll use to illustrate a bunch of points in algebraic topology. So up here we've got the cylinder. Of course, this is a surface with boundary. It's got you've got a boundary circle at the top and a boundary circle at the bottom. And then the other points are like proper surface points, which have neighborhoods that are homeomorphic to a disk. Cylinder, we can think of it, you've got kind of a circle in the xy plane, and the product of that with a like an interval from -1 to +1 in the z direction. So it's cylinder is homeomorphic to S1 across the interval -1, 1. And then here's the sphere, surface of genus 0, and a torus, the surface of genus 1. So all these, so far, these are all orientable surfaces. And we'll have various separate videos later that discuss some more elaborate features of their topology. And then here we have the Möbius strip. That's our kind of first example of a non-orientable surface. It's not orientable because if you kind of if you draw a little figure on here and then you move it all the way around the Möbius strip, then it will come out as a mirror image after you've been all the way around the strip. And then here we've got the Klein Waffle. This is again a non-orientable surface. This is formed by taking a cylinder, and then we sort of stretch the cylinder out, and we take a kind of neck as shown along here, and then we pass the neck through the side wall of the cylinder and then connect it up at the front, as we've got here. And of course, and then this sort of passing through itself, that's just like an artificial feature because we're trying to do this in three-dimensional space. The proper Klein Waffle doesn't have a self-intersection, but it has to live sort of in four-dimensional space. It's rather like this sort of normal situation, and we're more familiar with knots. Right? I mean, this is a trefoil knot. It's a subspace of R3, and it doesn't intersect itself. That's one of the basic examples in knot theory. But we typically have to sort of draw a picture of it in two dimensions like this. So here, and so when we project it down into two dimensions, then it's forced to intersect itself. But that's not what the real trefoil is like. It's just an artifact of our trying to draw it in two dimensions when it really wants to be in three dimensions. Similarly, going back to this Klein Waffle here, the real Klein Waffle lives in four dimensions and doesn't cross over itself. And then this here is what's known as the Boy's surface. This is like an immersed copy of the real projective plane, RP2. Again, the actual RP2 doesn't intersect itself, but if we try and put it in three-dimensional space, then we're forced to create these self-intersections, which you can see along these kind of seams along here. But apart from that, the intersections, those self-intersections, the Boy's surface is essentially the same thing as the real projective space RP2. Here's some more examples of closed orientable surfaces. You may remember these are classified by their genus. This is a typical example of a surface of genus 3 with like 3 handles. And here's one with surface of genus 2 with 2 handles, and here's a slightly different one, also of genus 2. So these two are homeomorphic to each other. We don't have like a computer picture of that, but you should be able to imagine that if you sort of stretch this out and thin out the waist and push and pull a little bit, then you can convert it to this one. And here there's again a surface of genus 4. It takes a little bit more imagination to see how this is homeomorphic to a standard surface of genus 4 with just a chain of 4 rings arranged in a line more like this. But with a little work you can imagine how to do that. And here are some more examples of closed surfaces of higher and higher genus. This one over here, well, if you think about this is basically a cube. We've taken a cube and we've kind of bent the edges and fattened them up, and so looks like this. Now if if you sort of draw it this direction, now if we sort of pull out the front ring and spread it out onto the plane, then you'll see that you've basically got a group of 5 rings all joined together. And so this is a surface of genus 5. And this is another picture which is essentially the same, fattened up cube. It's a surface of genus 5.